is yet another section where we're just doing applications of the chain rule. And so section 2.7, oops. I'm sorry, section 2.8. Section 2.8, related rates. And so problem on page 185. Problem number 6. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 40 millimeters? Okay, so let me write down what we have first, and then I'll draw things. So the radius of a sphere, I'll call it R, is increasing. So I'll put a plus sign because it's increasing at a rate of 4 millimeters per second. The diameter is 80 millimeters. None of my formulas that I know of involve diameters. So I'm going to write this as a radius instead. So if the diameter of your sphere is 80 millimeters, then your radius is 40 millimeters. They want you to determine how fast the volume is increasing. So they want to determine how fast is this volume increasing at when the radius is 40 millimeters and the rate of change of the radius is 4 millimeters per second. This is going to be in cubic millimeters. Per second. So let me draw this. I have here a sphere. Of radius R. And so the volume. So the real question is, does anyone remember the volume of a sphere of radius R? If you don't, later in this course, the last week or so of this course, we'll be able to actually calculate this. So even if you don't remember it, in the very last, using some of the last things that we do in this course, you can actually figure out what the volume is of a sphere. Okay, so using this, I want to answer that question. Okay, well, I want to figure out dv dt. So let's take a derivative. And so v equals 4/3 pi r cubed. And so let's take the derivative of both sides of this equation with respect to, with respect to t. And so I have dv dt is equal to, well, bring down the 3. So the 3's cancel here. So just get 4 pi r squared, subtract 1 from the exponent, times the derivative of what's inside, dr dt. So what you should notice is that the rate of change of the air of the volume of a sphere with respect to its radius is its surface area. Now let's plug in. So I want to figure out dv dt. Well, I know what r is. The radius, remember the diameter was 80. So the radius is 40 millimeters. And the rate of change of the radius, they give it to us as it was increasing at the rate of 4 millimeters a second. And so dr dt was 4. Oh, that's 256. So that's 4. That's 16 times 16 is 256. So it's 256 with 2 more zeros. 25,600 pi cubic millimeters. Oh, that looks kind of weird. Cubic millimeters per second. And that's the rate of change of the volume. So dv dt is 25,600 pi cubic millimeters per second. Any questions about that? So I'm actually going to do several of these, well, tons of these related rate problems, just so that they become second nature to you. Okay, so let's do the next problem. Problem number 12. So in problem 12, a particle is moving along a hyperbola, xy equal 8, as it reaches the point 4, 2. The y-coordinate is decreasing at a rate of 3 centimeters per second. How fast is the x-coordinate of the point changing at that instant? Okay, so we have here that the y-coordinate is decreasing at a rate of 3 centimeters per second. And that the we want to figure out how fast is the x-coordinate changing at that moment. When we are at the point 4, 2. So when x is 4, and this is going to be in centimeters, and y is 2. Where we're traveling along this curve. Okay, so let's do that. Maybe I'll draw the situation that's occurring. Because the answer is going to be so fast. Let's actually do that for 1 second to show you what's happening. Okay, so xy is equal to 8. So the graph of xy equaling 8 looks something like this. We're at the point 4, 2. And the y-coordinate. And so you're going in this direction. You're dropping at a rate of 3 centimeters a second. the question is, as you're going along this curve here, so you're dropping. Well, how fast are you going in the x direction? So if I look in the x direction, how fast am I traveling? Okay, so let's do that. Actually, maybe let me zoom in. Actually, let me zoom in here for 1 second. So I'm here at the point 4.2. And so I know that I'm dropping here at 3 centimeters per second. And then the question is, so this is dy dt. So I'm going down. That's why I'm below. So now the question is, well, what's dx dt? Okay. Well, let's figure that out. So xy is equal to 8. Let's differentiate both sides of my equation. And so I have, well, in order to differentiate this, I'm going to have to use the product rule. So derivative of the first, oops, what happened there? Sorry. This is derivative of the first times the second plus the first times, each of these are changing. You stupid. Let me do it correctly. The derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of 8 is 0. So now let's see if I can plug this in. So dx dt, don't know. Y, 2. So y here is 2. X, I know what x is, 4. dx dt, dy dt, I know that, -3. Okay. And so I have here that 2 dx dt minus 12 is 0. And so dx dt is equal to 6 centimeters per second. And so this is positive. So x is increasing. At the rate of 6 centimeters per second. Any questions about that? Okay. So let's do the next problem. 5 minutes. Oh, we probably have 5 minutes. Okay, so let's do the next problem. Problem 17. 2 cars start moving from the same point. One travels south at 60 miles per hour. The other travels west at 25 miles per hour. At what rate is the distance between the 2 cars increasing 2 hours later? Okay, so let me draw this situation. So first off, let me draw north, south, east, west. So I'll put a little compass here so I know where I'm going. So I'm going to say that this is north, south, east, west. Next, let me draw the other part of this. So one car starts moving, two cars are moving at the same point, one travels south. So one car here travels south at 60 miles per hour. So it's going to be traveling at a rate of 60 miles per hour. I'm not going to put that rate there. I'm going to say that the length here is y. The reason is that when I label these, I only want to put things that are remaining the same as numbers. Everything else, I'll use a variable. Next, the other travels west. Okay, so it's traveling west. So it travels, so the one traveling south is at 60 miles per hour. So 60 miles per hour. The other travels west at 25 miles per hour. Okay. At what rate is the distance between the two cars increasing 2 hours later? So now, oops. Well, actually, I'll get rid of the endpoint. So now I'll say Z. I'll call that Z. So I want to figure out Z at T, Z after 2 hours. Is it rate? So dz dt. So I want to figure out dz dt after 2 hours. Okay. Well, the first thing that I want to do is figure out, well, after 2 hours, how far apart are they? Well, actually, maybe I won't do that. I know I need to do that, but maybe you don't know why I need to do that yet. Okay, so let's just start and then continue until we find there's something that we don't know, and then fill that in so that we can proceed further. Okay, so only got 1 more minute. If I look here, this is a right triangle. So by Pythagorean's theorem, I have that a squared plus b squared equals c squared. Let me take the derivative of both sides of this equation. Notice that all the variables, all of these are variables. They all depend on t. And so I'm going to have to use implicit differentiation, the chain rule, and I'm going to have to be sure to write everything as derivatives of each of these variables with respect to time. So this will equal 2x dx dt plus 2y dy dt is equal to 2z dz dt. I can divide everything by 2 because there's a 2 in common everywhere. That will at least simplify my arithmetic very slightly. Now, I know dy dt. I know dx dt. And I want to figure out dz dt. But I don't know x, y, or z. So the problem is that there are things that I don't know yet. Because of that, I'm going to have to try to figure out each of those. So before I can do this, I've got to stop here and do some further calculations before I can plug into this equation. So first thing to note is that since we are traveling at a constant rate of, let's do the x first. Since I'm traveling at a constant rate to the west of 25 miles per hour, after 2 hours, I'll have that x is 50 miles from where we started. And this is since dx dt is equal to a constant 25 miles per hour. Next, well, if you're going 60 miles per hour, then if you're traveling at a constant rate of 60 miles per hour, then after 2 hours, you're going to have traveled 120 miles. And again, this is since the velocity is a constant 60 miles per hour. From here, I can figure out z. So x squared plus y squared equals z squared. 50 squared plus 120 squared equals z squared. So z squared is 2,500 plus 14,400, which is 16900. And so z is, that's 130. So z is 130. Of course, all of these are in miles. Okay, so now I know a lot more. So now I know x, dx dt, y, dy dt, z, but I don't know dz dt. Well, that's fine. I can solve for dz dt. Okay, so now that I have all this information that I needed, I can now redo this. So I have that x dx dt plus y dy dt is equal to z dz dt from above, from this equation here that we derived. And so let's just plug in. Well, I have 50 times 25 plus the 120 times 60 is equal to 130 times dz dt. Okay. And so that's 8450 is equal to 130, which is 6. Yeah. And so dz dt is 65 miles per hour. So your car is, so the two cars are moving apart from each other at 65 miles per hour. So the rate of the distance between the two cars is 65 miles per hour after 2 hours. So after 2 hours, they are speeding away from each other at 65 miles per hour. Any questions about that? Okay. Let me do problem number 18. A spotlight on the wall shines on a wall 12 meters away. If a man 2 meters tall walks away from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Okay, so I left this from before because I didn't want to draw anything. So let's see. Oh, yeah, I left all the drawings because I didn't want to redraw things. Okay, so you have here some man, and there is some spotlight. And so we have the spotlight here, and it's shining. Okay, and this spotlight is 12 meters on a wall 12 meters away. So this spotlight is 12 meters from this building. So I guess that's fixed. So maybe I'll just sort of say that. So this distance here is 12 meters. So you have this fixed distance here between the spotlight and the wall. So these are a distance of 12 meters apart. The spotlight and the wall. Now, this man, which is 2 meters tall, I will also assume that, it doesn't take him so long that he grows in height or maybe he shrinks in height. I will assume that he's always 2 meters tall. So I can actually fix that too. So that's his height is a fixed 2 meters. So that's also fixed. Now, he walks towards the building at a certain rate. So the length is going to be changing. So I'm going to have to put a variable here for that distance. And since he's moving, his shadow is going to get actually smaller and smaller. So this height of this shadow here, so this is supposed to be a shadow of this person. So this shadow here is going to change in height. So I have here, so I'm going to do this more abstractly. So rather than, have the stick figure of the man, etc., I'll just sort of say, well, this is the man. And it has a fixed height of 2 meters. Here's the spotlight, and here's the wall. I have a fixed distance here of 12 meters. I have a fixed distance, fixed height here of 2 meters. And I don't know, I'll call this distance here, that's changing, Z meters. And this distance here, X meters. And this Y meters. So the height of the shadow of the man on the wall is Y meters. And the speed at which, well, and the distance from the wall that this man is walking is Z meters. The distance of this man from the spotlight, we'll call it X meters. Okay, so we're just sort of fixing notation here. So in general, either you draw your, so how do you, I didn't tell you how to, so how do you read word problems? First thing to do is to quickly scan until you figure out what they're asking you. And here they're asking you this. So that's the question. And then once you figure out, so how fast is this length here decreasing? Okay, so we want to figure out the, how fast this height here of the shadow is decreasing. After you figure it out, what the question is, try to determine the data. So the data is he's 12 meters from the spotlight is 12 meters from the wall, and he is 2 meters high, and his speed is 1.6 meters per second. So this length is decreasing by 1.6 meters per second. And he is 4 meters from the wall. So I know the distance, 4, and the speed at which this is decreasing, 1.6 meters per second. Okay, so, oops. So let me write that. So let me write that down. So I know that the rate at which this is decreasing is 1.6 meters per second. Actually, I can do it 2 ways. So I can also think of it this way. This is a fixed point. And you're walking towards the wall. So I have a fixed point here. I'm walking towards the wall. Therefore, this distance here is increasing at the same rate that this is increasing. So these are going to be the same, going to increase at the same rate, since you're talking about a fixed point. And so I could also say that dz dt, dx dt, that's an x, that dx dt is 1.6 meters per second. But in this case, since you're moving this way, this length here is increasing, whereas this length here, because this is fixed, is decreasing. So again, I'm doing it relative to some fixed object. So here, this length is decreasing when you walk this way, but from here, then if you're walking in this direction, this length here is increasing. I also have that we know that this distance here, the distance from the building, is 4 meters. So I know that Z here is 4 meters. I want to determine the rate at which, how fast is the length of his shadow decreasing. So how fast is this decreasing? So you want to determine dy dt. And of course, that will be given in meters per second. Any questions so far about what I've done? Okay, so in general, once you've read a problem and you draw a picture. So once you've read the problem, figure out what they want, you draw your picture, you label it, remembering that when you label this, if in your picture it's fixed forever, then you put the number. If somehow the length will change, the variable will change during your problem, then you give it a letter. Each of these are changing, so we give it a letter. Either you will just see that there's some formula from what they're asking, or if it involves triangles, it will either be Pythagorean's theorem or similarity of triangles. In this case, it looks like similar triangles. And so let's look at these similar triangles. So this triangle is similar to this bigger triangle. And so I have this triangle. So this is a 2, and that's an x. So let's draw that. So I have here x2, and I have for my other one, well, this is y, and this one is 12. So I have here 12 and y. Okay, well, you have, unfortunately, 2 variables. So, well, maybe I'll want to reduce that so there's just 1 variable. Now, maybe I'll just keep it like that. It really doesn't matter. Oh, I see. Everything's in terms of, things in terms of z. Oh, so I know this in terms of z and that in terms of z. Oh, okay. So I want to know things in terms. So, well, let me just do it and then see what I need to know. Okay, so let's look here. It's at similar triangles. So I have here some similar triangles. So I can see that what I need to know, but I think it's better that I just go along and then, proceed. And then once I proceed, if it turns out that I need to know something, then at that moment, I'll try to figure it out. Okay. Rather than me seeing in the future, since I obviously know what happens in the future. Okay, so let's do this. So I have, let's say y over 12 is equal to 2 over x. Oops, where's the y? I didn't write the y down. This obviously is y. Okay, so I have y over 12 is 2 over x. So let me simplify that. So I have xy equals 24. Actually, what I can do is the following. I notice that, I notice that this length, the distance from this spotlight to the person, and the distance from the person to the building is fixed, because the sum of those is just the distance from the spotlight to the building, which is a fixed 12 meters apart. So I know that x plus z is equal to 12. Therefore, z is 12 minus x. And so I have, let's figure out what x is. I'm sorry. Let's figure out x. X is 12 minus z. Therefore, my x times y becomes x. Y is equal to 24. Okay. So now let me differentiate both sides of this equation. Let me use the product rule. The derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of 24 is 0. So now let's look back what we have. Well, we want to figure out, well, we know dz dt, so that's given. So dz dt is given. I know what y is. No, I don't know y yet. I don't know y yet. So I know y is equal to this. Okay. I guess I don't know y. And I know z. So I'm going to have to figure out y. Okay, so let's do that. Actually, you can figure it out from here. That y is 24 over 12 minus z. Then you'll have everything in terms of z, which you know. So maybe I'll write it that way. Well, no, let's yeah, let's write it that way. let me write it this way first, or let's write it this way. So I have y. And so I can write y as 24 over 12 minus z. dz dt plus 12 minus z dy dt. Okay, so now let's plug in everything I know. So I have here, I have here that z is 4 and dz dt is a negative 1.6. So let's use that. So z is 4. dz dt is a negative 1.6, which is 16 over 10, 8 over 5. Z is 4. Don't know dy dt, but I can figure out what dy dt is by solving. Okay, so let's do this. And so I have 12 minus 4 is 8. So I have a negative 24 over 8 times negative 8 over 5 plus 12 minus 4 is 8 dy dt. Okay, so the 8's cancel, so you get 24 over 5. Let's solve for dy dt. And so you have that dy dt is equal to, bring the 24 over 5 over, and then divide by 8. So your answer is a negative 3/5 meters per second, which is a negative 0.6 meters per second. And so the shadow is decreasing in length, in height. You want to say in height. By 0.6 meters per second. Any questions about this? Okay. I'm sure that every time I do this problem, I do it differently. I think this is the first time I've ever done it this particular way. So it's good to do a variety of different ways. Any questions about this? Okay. Let's do problem number 27. A water trough is 10 meters long and a cross section has a shape of an isosceles trapezoid that is 30 centimeters wide at the bottom, 80 centimeters wide at the top, and has a height 50 centimeters. if the trough is being filled with water at the rate of 0.2 cubic meters per minute, how fast is the water level rising when the water is 30 centimeters deep? Okay, so yeah, I was going to say, I probably don't, even though that's not, well, that's a pretty good picture. Okay, so I was like, I probably don't want to redraw things. So I still have this old picture. Okay, so you have here a trough. So there's some trough, and this trough looks like this. Isosceles. Come on. And so it's some isosceles trough. Okay, so something like this. Then you pour water into it. And so if you look at it a little bit more straight on, it looks something like this, which is the way I've drawn it here. So rather than looking at it, yeah, whatever. Yeah, now I messed it up. I did it okay. The second time I did it okay, but this time I didn't. Okay, so rather than looking at it lengthwise here, I'm going to look at it more forward-looking. You know, this is 10 meters, which is gigantic. It's way, way out there. And then this is just a little 30 centimeters wide. So it's not nearly as wide, it is long. So I've not really drawn it to scale, but that's okay. It's more important to do other things. So let's do this. So your water trough is 10 meters long. And so it's 10 meters long here. So it's really long. So it's a really, really long trough, 10 meters long. Has the shape of an isosceles trapezoid. So it looks like a trapezoid here. A trapezoid is a quadrilateral, meaning it has 1, 2, 3, 4 sides. It is isosceles, meaning that this angle here is the same as this angle. These two lines here are parallel, and it's isosceles. So, well, in order for this to be a trapezoid, these two lines are parallel. It's a quadrilateral. To be isosceles, then it means that these angles here are the same. Okay? It is 30 centimeters wide at the bottom. And so the width at the bottom is 30 centimeters. 80 centimeters wide at the top. And so this width here at the top is 80 centimeters. And it has a height of 50 centimeters. So this height here is 50 centimeters. The trough is being filled at a rate of 0.2 cubic meters per minute. So you have some sort of device where you're pouring water into this trough and filling it up. And so it's being filled up at a rate of 0.2 cubic meters per minute. You notice that this is in meters, this length is in meters, but these are in centimeters. So you're going to have to change everything to the same unit. Since I'm dealing with cubic meters, I don't want to change from cubic meters to cubic centimeters. So I'll change everything into meters. Well, There are 100 centimeters in a meter. Therefore, 80 centimeters is 0.8 of a meter. 30 centimeters are 0.3 of a meter, and 50 centimeters are 0.5 of a meter. So now I have everything in terms of meters and cubic meters per minute. Okay. So you want to determine how fast the water level is rising. So how fast is this level of water here rising when the water is 30 centimeters deep, when it is 0.3 meters deep? So first off, let me just look at this guy. So let's look at the isosceles trapezoid from the head-on view. Okay, good. And so if I do that, I have here that the bottom is 0.3 meters, the top is 0.8 meters, the height here is 0.5 meters. Next, we have water. This water has some height. I'll call it H meters. And the top of this has some length. I'll call it Y meters. Okay, so let V denote the volume of the water in the trough. And so whatever this volume is, well, all this blue, whatever this volume is of that water, I'll call that V. And now let's try to figure out some things. Since I'm filling this up and there's no leakage out, then the rate at which this water is increasing is the rate at which you're filling it, which is this. So therefore, I have that dV dt is a positive 0.2 cubic meters per minute. Next, we want to figure out how fast the water is rising. So I want to find the rate of change of this. So I want to determine dH dt. When? So when do I want to determine that? Well, I want to determine that when the water is 30 centimeters deep. When the water is 0.3, 30 centimeters we know is 0.3. And so I want to figure out when this height here is 30 centimeters. And let's rewrite this in terms of meters. So when H is 0.3 meters. Okay. Now, let's recall some things. This is really just a cylinder. So it's a weird looking cylinder, but it's a cylinder. You know, a cylinder, let's do a circular cylinder looks something like that. If you have instead, I don't know, maybe that is also a cylinder. It's you know, it looks the same as your base. Or maybe your base looks like this. Then it is a cylinder. So this is just a cylinder. And let's recall the formula or a tube. Cylinder sometimes has a tube. And so let's try to recall the formula for the volume of a cylindrical object. And so the volume of a cylinder. So suppose you have, let's see if I can draw it. Okay. There, just some sort of weird looking cylinder. And the area of the base is A and height is H. Then the volume of the cylinder is A times H. It's the area of the base times its height. Well, the base in this case is a trapezoid. So what the heck is the area of a trapezoid? So let's try to remember area of trapezoid. So I have here the following trapezoid. So let's call this length here B1 and this length here B2. And this height here H. So a trapezoid consists of two sides that are parallel to each other. So I have here two sides. And it's a quadrilateral. So there's in total four sides. So the area of a trapezoid is the average height the average length of the base times the height. And so it's the average of these two bases times the height. And that's that's the area, sorry. That's the area of a trapezoid. Therefore, let me call this length. Otherwise, I have two things called height. Let me call this L. Let's call this L. Otherwise, I have an L and an H. So let's just call that length there L. Okay. So now, let's look at the following. So I'm going to use similarity yet again. And so let's look at the trough. But like before, I'm going to just look at it at the end of it. So let's look at it straight on so that, the rest of the trough is in back here. But we can't really see it because it's hidden by this front face. So it's somehow the rest of your trough is in back of it. You just can't see it. So somehow the rest of the trough is there. You just really just can't see it. It's hidden. Okay, so my trough here looks as follows. It's supposed to be isosceles. Let's make it look more isosceles. Yeah, that looks pretty good. Okay, so it looks a little bit more isosceles. Well, let's see. The total height of this trough here is 0.5 meters. Okay. And the length of this base is 0.3 meters. The length of this one is 0.8 meters. Okay, so this is 0.5. Everything will be in meters. I'm not going to specify that. And this length here is 0.3 meters. And this is 0.8 meters. Now let me look at the water. Well, if you look here at the water, it also looks like an isosceles triangle. As a matter of fact, it looks like a similar isosceles trapezoid. And so let's draw this if I can. And these are supposed to be similar. Okay, so this base here is going to be the same for the bottom of your trough and for the bottom of the water. So this is going to be 0.3. Next, the height here is going to be given by h, because that's what we call it. And so that's going to be h, and this length here is given a notation, it's called y. So this is going to be h, and this is going to be y. Okay. So we have these similar trapezoids. I have that y over h is the same as 0.8 over 0.5. And so I have here that get rid of decimals. So 8h is equal to 5y. So now let's try to determine the volume of the water. Okay, so the volume of your water is going to be the area of this end here times this length. So we call that the volume of a cylinder looks like is the area of the base times its length, its height. Okay, so it's the area of the base times its length. Well, it's a trapezoid. So it's 1/2 B1 plus B2 times H. And then we still have that L. So let's try to figure this out. So it's 1/2 of, well, here it is. This, oh, it is this plus this. So y plus 0.3. And the height is h. And the length is 10 meters. Any questions so far? So the volume is equal to 10 divided by 2 is 5. Let's multiply 5 inside the parentheses. So that's 5y plus 1.5h. Now, five y is 8h, so I can use this fact. So that's 8h plus 1.5h. I can simplify this as 8h squared plus 1.5h. And so let's take the derivative. So let's differentiate this. And so dv dt, well, the derivative of 8h squared is 16h. Times the derivative of what's inside, dh dt, plus the derivative of 1.5h is just 1.5 dh dt. Okay. So now let's plug in, I guess. So dv dt is 0.2. We want to figure out the dh dt. And h here is 0.3. Okay, so let's do that. dv dt is 0.2. H is 0.3. Okay, so 0.2, that's 48, 4.8 plus 1.5, 6.3. And so dh dt .2 divided by 6.3 meters per minute. So the depth of the water is increasing at the rate of 2/63 meters per minute. Okay. Any questions about that?
Can you please scroll up a little bit, Professor?
Sure. Tell me how far.
Just a little bit more. Just want to get at the, yep, that's perfect.
That's it. Okay.
Thank you.
Okay. So, oh, I thought it was going to be much longer. Okay, so problem number 29. Gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter is a height, whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? Okay, so I didn't draw. Oh, I probably had a horrible drawing. Okay, so I didn't have a drawing, so I probably couldn't draw it nicely. Okay, so I have here somehow, oops. So you have a whole bunch of gravel. Okay. And it's dumped from some conveyor belt. Okay. Yeah, the conveyor belt's got to be further on, or it won't make it. Okay, so you have these pieces of gravel that are on, hopefully actually on the conveyor belt. They're on the conveyor belt, and they fall off into this, onto the ground, but they never get there because they now have this huge cone that's being created. And so these are traveling. So the conveyor belt is moving at a rate of, well, no, the gravel is such that the volume of the gravel on the conveyor belt is its density is changing by 30 cubic meters per minute. So what that means is that the volume of the cone will be increasing by, so this is some conveyor belt, 30 cubic meters per minute. So this is conveyor belt. And I have that this diameter is the same as this height. So the height here and the diameter are going to be the same. Okay, so somehow when we dump it, it's into a nice looking cone so that this height here is the same as its diameter. Okay, so let me redraw this. Let's first recall the volume of a cone. So if you have a right circular cone of radius r and height h, then its volume is 1/3 pi r squared h. Okay, good. We have here, in our particular situation, oh, and let's write down what we know. What do we know? That the gravel on the conveyor belt is such that it has, well, its volume is changing at the rate of 30 cubic feet per minute, which means that the volume of this cone is going to be the same as what's being dumped onto it. The volume of the cone will be increasing. You know, the volume is increasing because you're adding stuff to it. It's going to be increasing at the rate of 30 cubic feet per minute. And so I know that dV dt is equal to 30 cubic meters per minute. 30 cubic feet per minute, sorry. This is done in feet. And what else do we know? We want to figure out how fast is the height of the pile increasing when the pile is 10 feet high. So when h is equal to 10 feet. And I want to figure out how high, how fast the height is increasing. So I want to figure out dh dt when h is 10. Okay. So note in our particular situation for our cone, I want to write everything in terms of h, the height. So this is the height h. But recall that the diameter is equal to the height. Therefore, the radius here is 1/2 the height. And so the radius is 1/2 the height, since the diameter is twice the radius. Okay, so that says the volume is 1/3 pi r squared h. So it's 1/3 pi r, but what's r? 1/2 h. And so the volume, there it is 1/3 pi r squared h. But now everything's going to be in terms of h. So V is equal to 2 squared is 4 times 3 is 12. H squared times h is h cubed. So let's differentiate this. So dv dt is equal to, let's bring down the 3 out in front. Subtract 1 from the exponent, times the derivative of what's inside. This is the general power rule. Okay. Well, dv dt is 30. 12 divided by 3 is 4. And the height is 10. So let me simplify this. So I have 100 divided by 4 is 25. Divide both sides of your equation by 25. And so dh dt (30 divided by 25 is the same as 6/5. So this is 6/5 pi feet per minute. And so the height of the cone is increasing. Well, let's call it the gravel pile, height of the gravel pile. Is increasing at the rate of 6/5 pi feet per minute. Any questions about that? Okay. Let me do problem number 31. The sides of an equilateral triangle are increasing at a rate of 10 centimeters per minute, at what rate is the area of the triangle increasing when the sides are 30 centimeters long? Okay, so I have here some equilateral triangle. Let's call each of these sides x. X. So that's the length of each of these sides. Okay, so they're increasing at a rate of 10 centimeters per minute. Okay. You want to determine the rate at which the area is increasing when the sides are 30 centimeters. And so what is dAdt? Let's recall, well, say the area of a triangle. And so we have some triangle, let's say. Its base has a length of b and the height is, let's say, h. Then the area of a triangle is 1/2 base times height. Let's also recall a 30, 60, 90 triangle. And so we have the following. Two, one, red 3. Where this is pi over 3. Okay, so a 30, 60, 90 triangle. Note the following. I could have put 1 here, actually. Not that it really matters. Maybe I will write it this way. As a 1, 1/2, red 3 over 2. And so that's your 30, 60, 90 triangle. So now, let's look at our triangle, just x centimeters, and x centimeters. Let's call this height here y. Well, it really didn't matter that I put a 1 there by similarity. We could have written it as follows. X, 1/2 x, radical 3 over 2 x. So from what I just wrote above, notice that here's my x. Here, total length is x, therefore half of it is 1/2 x. Therefore, y here is just rad 3 over 2 x. Okay. So, area, 1/2 base times height. So the area of a triangle is 1/2 base x. Height We're at 3/2. Okay. So this is equal to, we're at 3/4 x squared. So let's differentiate this. So dA dt is equal to, bring down the 2, 4 divided by 2 is 2. So we're at 3/2 x dx dt. And so dA dt we're at 3/2 x. Well, x is 30 and dx dt is 10. And so this is just 150 we're at 3. And this is in square centimeters per minute. Any questions about this? Oh, so maybe I'll write it down. The area of the triangle this equilateral triangle is increasing at 150 rad 3 square centimeters per minute. Any questions about that? Okay, then. Well, I gave lots of space. Problem 33. Actually, somewhat similar to what we've done before. Well, they're all, after a while, they're all are going to seem very similar to what we've done. Problem 33. The top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. How long is the ladder? Okay, so you have this ladder leaning up against the wall. And, well, this actually is not going to change. So this won't change. You know, hopefully it's not a collapsible ladder or something. So the length of your ladder is not going to change. But I'm going to give it a name because I don't know what it is. So they haven't told me what the length of the ladder is. So I would put a number there if there were a number that I knew, but I just don't know what it is. So I'll call it Z. You are, well, so far away from the bottom of the ladder, so far away from the wall, and it's going to be moving away. So this changes, this X here changes, is changing in value. Similarly, Y is the height above the height that the wall, that the ladder is on the wall. And again, that's going to be changing because it's your ladder is falling down. It's sliding down the wall. Okay, so let's write some things that we know. So let's see. The top of the ladder, there it is, slides down a vertical wall. There it is. At a rate of 0.15 meters per second. So this guy, which is the height that your ladder is on the wall, decreases because your ladder is falling down. And so I have that dy dt is equal to a negative, well, 0.15 meters per second. Next, at the moment when the ladder is 3 meters from the wall. So this ladder is 3 meters from the wall, therefore x is equal to 3 meters. Next, we have that this slides away from the wall at a rate of 0.2 meters per second. And so this bottom of the ladder is sliding away from the wall. So it's this length here is getting larger and larger. So x in this case is getting bigger and bigger. And it's sliding at a rate of 0.2 meters per second. Okay. And of course, I'm going to assume that the ladder is not collapsing. So I'm assuming that z here is constant. Okay. And you want to figure out what is z equal to? Well, I have here Pythagorean's theorem. And so I have that a squared plus b squared equals c squared, or in this case, x squared plus y squared is z squared. So I know x, I want to figure out z, but I don't have a value of y when x is 3. Okay, so let's do this. So let's differentiate both sides of my equation. So I have that 2x dx dt plus 2y dy dt is equal to 2z dz dt. You cancel out all the 2's. X dx dt, y dy dt Z dz dt. Okay. So x is 3 dx dt 0.2. So 3 times 0.2 times, well, y. I don't know what y is yet. dy dt. dy dt is negative 0.15 equals z. Oh, I don't know z yet. Times dz dt. Well, dz dt is 0. Okay, so let's figure this out. Oh, and so since this is 0, since dz dt is 0, it didn't really matter that I didn't know what z was. And so I get 0.6 minus 0.15y equals 0. And so y I can solve for. It's equal to 0.6 divided by 0.15. You can divide everything by 3. It's equal to 2/5. Ooh, 60 divided by 15 is equal to 4. Sorry about that. That was incorrect. And so this is 4 meters. Okay, so now let's try to figure out what we wanted. So I have here x. I have here y. I want to figure out z. I can use this to figure out z. So x squared plus y squared is z squared. And so z squared, 9 plus 16, 25. So z is equal to 5. Okay. So in this case, we have that the ladder is 5 meters long. Is that feet or meters? Everything's in terms of meters. So it's 5 meters long. Yeah, that's a semi-normal length. Any questions about this? It's actually slightly tall. 15 feet is kind of tall. Okay, so it's a long ladder. Let's do problem number 41. Two sides of a triangle have lengths 12 meters and 15 meters. The angle between them is increasing at the rate of 2 degrees, oh, I hate you, per minute. How fast is the length of the third side increasing when the angle between the two sides of fixed length is 60 degrees? So, since I have a little picture here, I left it. And so I have a triangle. So this is a nice triangle. And they have lengths of 12 meters and 15 meters. And I just called the other one Z meters for the heck of it. And I have that the angle is increasing at some rate, 2 degrees per minute. So I call this angle here theta. Of course, theta will need to be measured in radian measure rather than in degree measurement. And we want to figure out when the length of, how fast is the length of the third side, z, increasing, when the angle is 60 degrees. Okay, so let's do this. First, I have that I want to determine, well, I have that, and the angle between them is increasing at this rate. So I have that d theta dt is equal to 2 degrees per minute. Okay. So I'm going to have to convert that to radians. So this is 2 degrees over 1 minute, I guess. There are 180 degrees in pi radians. 180 divided by 2 is 90. So this is pi over 90 radians per minute. Okay. We want to figure out dz dt when theta is 60 degrees. I probably actually don't even need to convert that, but I will. And so 60 degrees, of course I already did this before, but it's pi radians over 180 degrees, which is pi over 3 radians. And I want to determine how fast the length of the third side is increasing. So I want to figure out dz dt. Okay. So in this case, it's not similar triangles or anything else. It's a formula that you're supposed to know, relating these and this. So relating the length of a side opposite an angle with the length of the adjacent sides and the inscribed angle. Well, let's recall the law of cosines. So the law of cosines say, and I don't care how I draw this, but let's say A, B, C. So the only thing is I want to be sure that I don't do it with a C in there because my C's look the same. So I'll do it with an A. So law of cosines says that A squared is equal to B squared plus C squared minus 2BC times the cosine of A. So that's the law of cosines. So I know here some things. So in this formula, I know B and C. So that's good. I know theta, and I know d theta dt. Okay. And I just want to determine dA dt. So I just want to do that. Okay. So I probably have most everything I need, except I probably also need this length here. I probably need this length here. Even if I don't, I'll just figure it out. So I probably need that length. So I have that z squared is equal to 12 squared plus 15 squared minus 2 times 12 times 15 cosine A. Oh, let's call it theta, since that's what we called it here. Okay, so, but we're going to do this for 60 degrees. I want to figure out what this length is at this particular time. Okay, so I want to figure out what this is when we have that my theta is 60 degrees. Ooh, actually, let's leave it at theta for a second. Let's leave it at theta for a second before I do that, because everything's constant here except for z and theta. So this will be a formula that I can differentiate. So let me leave it in this form for a second. So z squared equals 144 plus 225 minus 360 cosine theta. So z squared equals 369 minus 360 cosine theta. Okay, so this formula is true for all z and theta in this particular case. So if I differentiate this, I will need to know z. So let's figure out z first. So z squared equals 369 minus cosine minus 360 cosine of either you want to write it as pi over 3 or as 60 degrees. Doesn't really matter in this case. So I'll say pi over 3. The cosine of didn't I have it here somewhere? Here it is. The cosine, so I have it right here in the previous problem. The cosine of pi over 3 is 1/2. So this is equal to. So I just said that this is 1/2. So subtract 180. So 189. So z is the square root of 189. which is, you can divide by 9, that gives you 9, that's 21. And so 3 rad 21. It's plus or minus, but of course, we're dealing with lengths here. So I'll just give you the positive answer. So now I can differentiate this. So if I differentiate, if I take z squared equals 369 minus 360 cosine theta, and if I differentiate this, I get the following. I get 2 z dz dt. Derivative of 369 is 0. So minus 360 times the derivative of cosine. Well, derivative of cosine is minus sine. So that changes the sign to positive. Changes the negative to a positive. Times the derivative of what's inside, d theta dt. Okay, so divide by 2. Plug in z, and so I get 3 rad 21 dz dt. Well, I guess that's what we're trying to figure out is dz dt. (180). The sine of pi over 3 times d theta dt, which is pi over 90. It was 2 degrees, but now it's pi over 90. So pi over 90. Okay, so this is equal to 180 divided by 90 is 2, so this is 2 pi. The sine, we just had it over here. Here it is. Oops. The sine of pi over 3 is rad 3 over 2. Obviously, the 2's are going to cancel. So let's divide both sides of my equation by 3 over rad 21. So this is pi. 21 divided by 3 is 7. So this is 3 rad 7. And this is in meters per minute. Meters and minutes. Okay, so that's meters per minute. Okay, so we have that the length of the third side is increasing. at the rate of pi over 3, we're at 7 meters per minute. And that's your answer. Okay. Any questions about that? Okay, then let's do the next problem. That's probably the last problem, or maybe one more after that. Problem 47, a plane flying with a constant speed of 300 kilometers per hour passes over a ground radar station at altitude of 1 kilometer and climbs at an angle of 30 degrees. At what rate is the distance from the plane to the radar station increasing a minute later? Okay, so we have the following situation here. We're in some airplane and we fly over some radar station. We are traveling at a rate of 300 kilometers per hour. We are at an altitude of 1 kilometer above the radar station. And we climb at 30 degrees. We want to figure out the rate that the distance from the plane to the radar station is changing after 1 minute. Okay. So let me draw this. Actually, I've already driven it. I drew it here, so I don't need to redraw it. So I'm going to say that this, so here is my airplane, originally over the radar station. Airplane over radar station originally, which is 1 kilometer above the radar station. We then go up at an angle 30 degrees. So if I look here, I'm going up at an angle of 30 degrees. I then want to figure out what this length is. I'll call it Z. I don't know what that is. After 1 minute. Oh, how horrible. They've got degrees and they have minutes and they have hours. So I have to convert a few things. So if this is 30 degrees, since this angle here is a right angle, 30 plus 90 is 120. So this full angle here is 120 degrees. Okay, so let's do this. And I guess I just call this angle theta, because it looks nice. Okay, so I have here the following information. We're increasing at a rate of 300 kilometers per hour. So dx dt is 300 kilometers per hour. Theta is 120 degrees, which when converted to radians, divide each of those by 0, get rid of that, so it's 12 over 18, divide by 6, so that's 2 over 3. So 2 pi over 3. Okay, and we want to figure out dz dt. Okay. Use the law of cosines yet again. So from the law of cosines, just like before, we have that a squared is equal to b squared plus c squared minus 2ab, 2bc cosine of a. Okay. So let's figure out what that gives us. So I have z squared is equal to b, which is, I don't know, let's call it 1, plus c, I'll call it x, minus 2b c cosine a. Okay. And so I have z squared equals 1 plus x squared minus 2x. Oh, and let's call that theta. Let's call that angle theta. And well, that's always going to be fixed. You're never going to change that. So this angle is always 120 degrees. It's always 2 pi over 3. So you're not changing course direction or anything. Okay, so let's figure out what cosine is of 2 pi over 3. Well, let's recall. 2, 1 rad 3. And this is, well, pi over 3, 60 degrees. Okay, so if I look, put this in my standard position. So if this is 2 pi over 3, and this angle is pi over 3. Okay, so cosine 2 pi over 3. So cosine is going to be negative in the second quadrant. And cosine by its reference angle is 1/2. So cosine 2 pi over 3 is equal to a negative 1/2. Okay, so let's simplify this now. So I have z squared equals 1 squared equals 1 plus x squared Okay. So let's plug in a negative 1/2 here. So if I plug in negative 1/2, that cancels this. So I just get a plus x. And so let's let's figure out what x is. Let's determine x. And z, actually. after 1 second. After, not 1 second, it's 1 minute. After 1 minute. Okay, so this is traveling at 300 kilometers per hour. 1 minute is a 60th of an hour. So therefore, the distance that this has traveled is 1/60th of the 300, which is 5 kilometers. So let's figure out what Z is. $31, okay. And so Z is equal to the square root of 21 kilometers. Okay, so now let's try to determine, whoops, sorry. Let's try to determine, let's take the derivative of both sides of this equation. So let's try to determine dz dt. Z squared equals, I don't care, 1 1 plus x squared plus x. And let's take the derivative. Oh, come on. Let's take the derivative. So differentiate. And so this is equal to 2z dz dt. Derivative of 1 is 0. Derivative of x squared is 2x dx dt. Derivative of x is dx dt. And let's fill this in. So I know what z is. Well, I know what z is. Radical 31. I do not know dz dt. Oops. I know what x is. We just figured that out. X is equal to 5. It's right there. And dx dt was equal to 300, I think. Yeah, 300. And dx dt was 300. So 2 rad 31 dz dt. That's 3,300. Let's divide both sides of my equation by 2 rad 31. So dz dt is 3,300 divided by 2, which is 1,650. over rad 31. And this is in kilometers per hour. Okay, so that's what we want to figure out. So I have that the distance the airplane to the radar station is increasing at the rate of 1,650 over rad 31 kilometers per hour. Any questions about that? Okay. Oh, I still have one more. Oh, that's got to be the last one. Okay, so let me do problem number 49. A runner sprints around a circular track of radius 100 meters at a constant speed of 7 meters per second. The runner's friend is standing at a distance of 200 meters from the center of the track. How fast is the distance between the friends changing when the distance between them is 200 meters? Okay, so you want to figure out how fast this distance is changing between the friends. So I have here, so we have a circular track. Okay. And the circular track is 100 meters in diameter. You have a friend standing a distance of 200 meters from the track. Okay. And then you ask, well, suppose you're here running. How fast is this distance changing when you're 200 meters apart? Well, either you could be, let's say you're running it around this way. So either you could be running away from them, or if you're 200 meters, so this is also 200 meters, or you could be over here, in which case you're going along the track that way. And so you could either be coming towards your friend or away from you. Let's see here, wait. You're standing between distance between them. So it doesn't say, it just says the distance between them is 200 meters. So it doesn't say if you're running towards your friend or away from your friend. So I really won't know the sign. So I'm not going to be able to figure out the sign. Okay, so let me draw this. So right now, I haven't given you any labels yet. So there are no labels here. For one thing, this is changing. So I can't really write 200 on my my picture. But my official picture is going to look a little different from it because I'm going to coordinatize this. So I'm going to coordinatize everything. So let's see. Yeah, let's do it so it doesn't move back and forth. So let's coordinatize this. Okay, so let's do this. Where the center is at the origin. So this is 100. Okay. And this is X. And so you're going to be here at 200. So your friend is at 200. And you are somewhere on the track. I'll put you in the first quadrant. Again, you could have been in the fourth quadrant. By the way, you can't be in the second or third quadrant because you're only a distance 200 from the other, from your friend. Okay, so this distance here is going to be changing. So I'm going to call this Z. And this is in meters. So each of these are meters. And this distance here is still 100 meters because it's a radius. And I'll call this angle here theta. And I'll call this length here S. Okay, good. Well, maybe I'll put the other. This is 100, negative 100, and negative 100 at each of these locations. Okay, so whoa. Sorry about that. Okay, so let's see. Let's put in some of the facts here. Well, I already given you some. So the radius of the track is 100. That's already in the picture. And he's running around the track at a constant speed of 7 meters per second. He's on this track. And he's going in a circular motion. And so the distance that he travels along here is 7 meters in 1 second. So his change in arc length is 7 meters per second. So I'm really looking at the change in the arc length. That's why I put S there. So I have here that ds dt is 7 meters per second. And we have that z, we want that to be also 200. So we want that this distance here, here, that this distance here is 200. And we want to figure out how fast this distance is changing. How fast is this distance here changing? So what is dz dt? Okay, Well, first thing to note is the following. Let's recall things about the arc length. So if I have some angle theta here, some radius r here, and some arc length s here, I have that s is equal to r theta, as long as you're measuring everything in terms of radian measure. So in our particular case, the radius is 100. So let's differentiate both sides of my equation. With respect to t. So ds dt is 100 d theta dt. I know what ds dt is. ds dt is 7. And so I have 7 is equal to 100 d theta dt. So d theta dt is 7 over 100. Next, let's use yet again the law of cosines. So if I use the law of cosines, and maybe I'll just sort of say the law of cosines. I don't care what I put it. I think I put in terms of a's before. A squared equals b squared plus c squared minus 2bc cosine of a. 2bc. Okay, so let's say A, B, C. Okay, so in this particular case, we have z theta 100 and 200. So those are fixed things. So those are things that are fixed. And so I have that z squared is equal to 100 squared plus 200 squared minus 200 cosine theta. And so z squared is equal to, that's 10,000 plus 40,000 is 50,000. Yeah. Minus, that's 40,000. 4 zeros, yeah, 40,000 cosine alpha, cosine theta. Okay. When I differentiate, I need to know the cosine of theta. So I need to know somehow the cosine of theta. I could proceed like I did previously, as if I didn't know where I need to land, but I know that I'm going to need a sine. So let me try to figure out that. Okay, so I want to figure out when z is 200, what's theta? What's sine of theta? So 200 squared is 50,000 minus 40,000 cosine theta. And so 40,000 is 50,000 minus 40,000 cosine theta. Okay, so I get a negative 10,000 is negative 40,000 cosine theta. So if you divide, you get 1/4. Let's square both sides. So I get that cosine squared is 1/16. And so sine squared is 1 minus cosine squared. Is 1/16. So sine squared is 15/16. So sine of theta is plus or minus, I don't know which one it is, square root of 15 over the square root of 16, which is 4. Okay, so, oh, and that's why I don't know. I don't know if it's positive or negative because I don't know if you're coming or if you're going. So I don't know if you're above or below the x-axis. So I don't know which of these you're doing. By the way, just so the other signs were definite, I assumed that you were going in a counterclockwise direction, so that at least I knew the sign of theta, that d theta dt was positive. I made you go in a counterclockwise direction. Okay, so now, well, I have this. If I differentiate, knowing this, I can figure out what dz dt is. And so let's determine dz dt. There. Okay, so let's try to determine dz dt. And so let's differentiate. Z squared equals 50,000 minus 40,000 cosine theta. So I'm just taking this formula and differentiating it to give me this. Okay, so two z dz dt is equal to, well, the derivative of constant is 0. So derivative of that, 50,000 is 0. Minus 40,000 times derivative of cosine, which is a minus sign. And so that'll give you a plus 40,000. The sine of theta times the derivative of what's inside. Derivative of theta is d theta dt. Okay, so now let's plug in things we know. What is z So Z is 200. So I know that. And what's the sine? And so the sine of theta I know is that. Okay, so let's plug this in. So I have 2 Z, which was 200, dz dt is equal to 40,000 sine of theta, which is plus or minus rad 15 over 4 d theta dt. What was d theta dt? There it is. So d theta dt is 7 over 100. Okay, so this is equal to, I can simplify this, 400 dz dt divide by 400, so you get 100, and times 7 is 700 rad 15. Okay, so divide by 700 rad 15, the hundreds cancel. So dz dt is equal to plus or minus 4 over, divide by 400. 7 rad 15 over 4. So, and this is going to be in meters per second. Well, that's going to be it. And so this says that the distance, again, I don't know if it's coming or going, so I'm just going to have to state it in a way where I don't say where it's, if you're approaching or going away from it. So I'll just say the distance between the friends is changing at the rate of 7 rad 15 over 4 meters per second. So I'm not saying if it's increasing or